Hello, ladies and gentlemen. In my astronomy class, hope you do well and all your classes also goes well in this hard situation. So I hope and it will be overcome all of us in this hard situation. So I'm going to talk about chapter 6. Here is two things that I have to tell you. If you use 11 edition, there is one difference between 11 edition book and 10th edition book. In 10th edition, chapter 6 that you have it in your PowerPoint, it's same as chapter 5. In 11 edition, chapter 6 is chapter 6. Okay, so in 10th edition, chapter 5 is chapter 6 of 11 edition, and in 11 edition is chapter 6. So what is difference is in 11th edition they add before chapter 6 they add one chapter which is chapter 5. It is actually discovering the universe. It's talking about exoplanets and formation of planetary systems. So what is differences between 10, 11 and 11 edition? Nothing. In 11 edition, just they split actually chapter 5 to two chapters, 5 and 6. But in 10th edition, both chapter 5 and 6 in 11 editions are inside chapter 5. So I'm going actually over chapter 6 in 11 edition, okay, which it is same with chapter 5 in 10th edition. Okay, hope you got it, and if it's not make sense, please email me, let me know. In chapter 6 we will learn about formation of solar system. What is formation of solar system means? If we go back, if we do radioactivity of uranium and carbon also, we will see that our planet Earth, the Sun, and even the other planets by spectrophotometry, we can see that the solar system formed 4.5 to 4.6 billion years ago. So what I have, our solar system formed actually 4.6 billion years ago. My apologies because I never use these pens honestly to write on the screen. So if you see it's not good handwriting, so forgive me please. So our solar system formed 4.6 billion years ago, but a theory which it's talking about formation of the universe, which it is so far, I don't say it's 100%, but so far is accepted about formation of our universe. It's theory which is called Big Bang theory. Again, it's not 100% correct. most of the scientists or physicists, they accept it, and also we have some physicists that they don't accept this theory. But it is accepted overall, we can say so far in the science. It might change many things because in astronomy we cannot say 100% this is correct and this idea is wrong. No, many things change actually because some new experiments, some new machines, some new theories comes that they reject the old theories also, okay? But what we accept, what your book goes, what is accepted so far, it's Big Bang theory. And the Big Bang theory, which it happened actually 13.8 billion years ago. So this is 13.8. Some books goes with 13.7. Your book goes with 13.8. So let me go 13.8 billion years ago. Okay. The Big Bang theory, it says the Big Bang happened 13.8 billion years ago by phenomena which is called singularity. What is singularity means? It's not easy topic, this one to understand it, but I will go very briefly. Singularity means is when volume goes to very small, goes to zero. When volume goes to zero, we know one equation which is called density. Okay, what is definition of density? Of course, we have in physics we have 6 different density, but this is called mass volume density. Mass volume density. So density is mass divided by volume. We showed by D, or majority of books in physics, they go by this symbol. It's called rho, but it's okay, you go by D. So D is equal mass divided by volume. So guys, here we see if volume goes to zero, therefore your density will be mass, correct, divided by a number, which this is infinity. This is the symbol of infinity, showed by this. Okay. So what we see, volume goes to very small amount. So volume decreases. And when volume decreases, density goes to very high amount. So when density goes to infinity, okay, what is happening, there is two important quantity, which is called pressure and also temperature. So when density increases, pressure and temperature both, they increase a lot. Okay, when pressure and temperature increases, imagine at the single point, what is happening? Explosion happen. So the explosion that happened, we say time starts actually from this. So this is starting of time. Okay. Now, so this explosion happened when 13.8 billion years ago. 13.8 billion years ago. All right. Now, so when Big Bang happened, your book says when Big Bang happened, all the universe expanded, and also the only particles, the only atoms, the only element that was found in Big Bang after Big Bang was hydrogen and helium, which is number 1 and number 2 on periodic table. But if you remember, in the class I told you that, guys, when pressure and temperature, because of singularity, increases, it increases to 30 to 35 billions Kelvin or Celsius. So at a certain time, when this temperature pressure increases, what is happening, because expansion, pressure and temperature, every single micro nanosecond decreases. When this happens, temperature and pressure decreases, it is good conditions to form electron. So 11 seconds after Big Bang, electrons form. At the end of 46 seconds later, protons forms. Then positron, which it is anti-electron, forms. So like 56 seconds after Big Bang, electrons and protons, they join together and they make hydrogen. This process goes, temperature and pressure decreases until at the 176 seconds after Big Bang, the two protons and two electrons, they join together, and also neutrons, and they form helium. So hydrogen formed at the beginning, then helium formed at the end of 176 seconds after Big Bang. Maybe the numbers are not very correct because little differences we see between books, but overall it says the first 3 minutes. So in the first 3 minutes after Big Bang, two main gases, which they are hydrogen and helium, they formed and they all covered all universe. Spectrophotometry shows that hydrogen and helium are the most abundant gases in the universe. 98%, these are very important, please pay attention. 98% of observed mass, 98% of observed mass is hydrogen. 98% of observed mass is hydrogen and helium in our universe. H2, so this is H2. Let me correct it. and this one He. H2 means is hydrogen, He means is helium gas. So 98% of observed mass in our universe is hydrogen and helium. Only 2% is other gases like oxygen, nitrogen, sodium, and methane, and also ammonia. So only 2% is other gases. Like what? Like oxygen, like nitrogen, like methane, and also like ammonia. Okay, so what we see, Big Bang formed 13.8 billion years ago, but our solar system formed 4.6 billion years ago. So if you do 13.8 minus 4.6, it comes something close to 9.2. Let's say 9, okay? Let's say 9. 9 billion years after Big Bang, our solar system formed. What is our solar system? The sun, all planets, Kuiper belts, Oort belts, beyond Neptunian, Pluto, inner planets, outer planets, asteroid belts. So these all formed 4.6 billion years ago, not 13.8 billion years ago. So what had happened during this 9 billion years? So let's see. So guys, let's say, let me see. Okay. Let's say, no. Let me do, all right. Let's say this is our universe. So when Big Bang happened, actually, all this universe, because of expansion, it followed by two main gases, hydrogen and helium. So this is 13.8 billion years ago. Okay, so it's all two major gases. It's all hydrogen and helium. So I'm telling you as a story, so please listen it. It's good to understand it. So 13.8 billion years ago, when hydrogen and helium covered all entire the universe, couple 100 million years after, so I'm not talking about how the stars formed. This will be in chapter 11 and 12. So some stars, they formed in our universe, okay? And also because of gravitational force, these stars, they collect close together. So finally they make what? Galaxies. So this is galaxy. Not one galaxy, but many, many galaxies. All right. And we have, of course, in this universe, in somewhere, we have main more gases in some areas, okay, which this gas is hydrogen and helium. And this area, actually, the temperature was very low. So how much was temperature? It was like 10 degree Kelvin. So temperature was like 10 degrees Kelvin. 10 degrees Kelvin is like negative 260, let's say, Celsius. This is something like negative 400 Fahrenheit. So temperature of this section, which is all gas, collection of gas, what kind gas is? It's hydrogen and helium. The temperature in this round was negative 400 Fahrenheit. Okay, so later you will see I call this one solar nebula. Why do we call it solar nebula? Because our solar system formed in this area of universe. Okay, if you go on other stars, on other constellation like Orion constellation, we do have Orion Nebula. We do have what? Orion Nebula. Unfortunately, this situation didn't and doesn't let us to take you to night observation. It was very good time. It is very good time at this time to could observe Orion Nebula, which we did it last year actually, because it's the best time in spring to could observe Orion Nebula by telescope. What is nebula? It's all gas. Okay, let me show you what is the picture of that section. So here you are. This picture, this one, it's nebula. It is nebula. So what we had, solar nebula, like Orion Nebula, like we have Crab Nebula. So what is nebula? It's the location of collection of hydrogen and helium gas in that part of galaxy, right? So guys, the solar nebula, this is important. Solar nebula, the diameter, so D is not density here, it's diameter. Diameter was close to 1000 AU. What is AU means? Astronomical unit. It's the average distance from Earth to the Sun. It's called 1 AU. So imagine 1000 times of this distance was all collection of gas, hydrogen and helium, which it was called in that time solar nebula. Okay, now guys, one of these stars, one star actually was close to this collection of gas, hydrogen and helium. What is happening? This star actually, it's called nearby star. Nearby star. Let's say this is a nearby star, okay? What is happening, guys? It dies. What is dying means? when star actually gets old, maybe it was small, but it was close to this section. So because of nuclear process, this star explodes because of its mass, because of its age, because of its chemical composition, because of uh, different reasons, we can say. This star explodes. When this star explodes, because of fusion, it creates huge, big amount of force and winds. What is that wind means? It's all particles, heavy particles. So when star actually explodes, the explosion of star, it's called supernova. So what is supernova? It is nuclear process that star, because of fusion, in that explosion makes heavy elements like what? Like iron, like carbon, like oxygen, like uranium. All right? So when this star actually explodes, a lot of heavy elements, they comes toward this section which is called solar nebula. Right? So supernova actually forms heavy elements which they come by wind. That wind is called supernova's wind. Okay, so they comes, it is force actually, so this one is force. So when they comes toward this section of space which is in solar nebula, they start to rotate the system. So the system of solar nebula starts to rotate because of supernova. So what is supernova? It's force ejected by fusion of nearby stars close to solar nebula. So this force, excuse me, is caused to make rotation. So guys, rotation is the main reason, first of all. Oops, what is that? So rotation is the main reason in that it formed actually by this force. Then we are going to have what? So we learned about solar nebula, that it's collection of collection of hydrogen and helium in certain area of space in our galaxy, and the temperature of that section was 10 Kelvin, like negative 400 Fahrenheit. Therefore, in the solar nebula, rotation gravitational force, or let's say gravity. So the particles starts to rotate. The particles starts to rotate in that system. And in the same time, because of gravity, these particles, they were moving toward the center because of gravity. What is happening when these particles, they, because of gravity and rotation, they move toward the center of the system? Guys, when you have higher density, when you have more particles that they rotate in one part, in one section, of course, we are going to have more collision. We are going to have, let me check your book to see what section I am. Yeah, this is section 6.1. So in collision, so collision increases, pay attention. So rate of collision because of rotation and gravity increases. Where? Inside solar nebula. When collision increases, we have another quantity which increases. What is that? It's temperature. So rotation increases, gravity pulls everything toward each other. And during this collision increases, when collision increases, temperature also increases. So what is happening, guys? At the center of this big space, which is called solar nebula, okay, here at the center, temperature increases, rate of collision increases, rotation, of course, is more because of angular momentum, So when temperature increases, the particles join together. They stick together, actually. That is caused to increase density. So density increases at the center of solar nebula. When density increases, in the same time temperature increases. In the same time, again, rate of collision increases. And this all happens because number one is gravity. Number two is conservation of angular momentum, which is caused to make what? Rotation. So gravity is number one. That's why a gravitational force is the first fundamental force. So gravity is caused to collect as a group. Then angular momentum because radius changes, speed of rotation increases. That is caused to make more rotation. Rotation is caused to make more collision. Collision is caused to make more temperature and, of course, density. So density increases, temperature increases, rotation, gravity, collision, everything increases. So what we are going to have at the center of this system, which is called solar nebula, okay, temperature increases. When temperature increases, it reaches to 7 to 8 million Kelvin or Celsius, doesn't matter. This section acts like huge amount of heat source. We call it protosun, not the sun. Pay attention. Temperature is 7 to 8 million Kelvin, and protosun makes heat not by nuclear process, makes heat by only collision. Okay, which it will be, of course, more in the part of what? Infrared spectrophotometry spectrum. What is happening in the same time as protosun forms, guys? We have heavy elements, collection of heavy elements on different levels. Collections of heavy elements on different levels around protosun. Collection of different elements, heavy elements, I mean like helium, like iron, like carbon, uranium. But because of angular momentum, on farther distance from protosun, gas, hydrogen and helium are remained. What is happening? Again, because of rotation, because of density, because of collision, these hydrogen and heliums, they make a big group. Because of gravity, they gather too close to each other. Okay, like on same level with different locations. Time goes. So this doesn't happen in 1 day or 1 hour. It takes 100 million years, 200, 300 million years. Finally, what is happening? These small planets, they are called planetesimal. I think it's double L. They are small planets. What is happening again? Time after time, because of temperature, because of collision, because of density, what we are going to have we are going to have this. At the center, temperature increases. And on different levels, this is not good. On different levels, planets form. Okay. You see, like on the first level, maybe we had 3, 4, 5 small planets. On the second level, we had 2, 3, 4 small planets. On third level, we had 3 or 4 or 5 or 6. We don't know, small planets. Because of collision, because of gravity, these small planets, which they are called also right now, also in other systems, star systems, they were called planetesimal. That means small planets. Those small planets, because of gravity, they stick together. They make bigger planet. They make one planet actually. So temperature increases. What we are going to have at the middle, at the center, protosun converts to the sun. I'll tell you what is the sun in the next page. Then on first level, the planet Mercury forms. So these small planets, they join together, they make Mercury on the first level. On the second level, what we have? Venus. On third level, what we have? We do have Earth. On the fourth level, what we have? We have Mars, correct? And then what we have? We have Jupiter. And then what we have? We have Saturn, correct? And then we have Uranus. And then we have what? Neptune. But you may say, which planet formed first? What is your answer? The answer is Jupiter. Jupiter was the first planet formed. Actually, if Jupiter was 75 times massive than it is today, it would be a star. So in reality, Jupiter missed to be a star. Then our solar system would have 2 stars. We would have double stars. One would be Sun, the other one would be Jupiter, but it's not, fortunately. I believe if that would happen, we would not have life on the planet Earth, because too much solar system, ultraviolets. We would not have daytime and nighttime. Maybe it was always night, or maybe it was always day. Majority of stars that we can see, 92% of the stars that we see them in our skies, they are called binary systems. We might see them only by one particle as one star, but no, they are 2 stars. They are 2 stars, but they orbit around one center. So let me explain you that. So binary system it's one star and one star. So two stars, they orbit around a point which is called center of mass. So this star orbits around this point, and this star orbits around this point. This system is called binary system. But our solar system is not binary system, it's one star. So Jupiter would be star if it was 75 times massive than it is today. Jupiter actually makes energy, but it doesn't make energy by fusion like our sun. It makes energy by collision, by radioactivity actually. The Jupiter in the core has uranium, so that uranium makes radioactivity. So it gives a lot of IR. Okay, so this is how our solar system formed. There's a lot of video in YouTube, you can watch them. So now I am going over the sun, how protosun actually converted to the sun. Watch guys, when temperature at the core of solar nebula, when temperature in the core of protosun reaches to 10 million Celsius or Kelvin, when temperature at the core of solar nebula, when temperature in the core of protosun reaches to 10 million Kelvin, then this, oops, come on, then this is good and enough temperature to what? To fuse hydrogen to helium. So hydrogen converts to what? Helium. When temperature reaches to 10 million Kelvin. This is enough temperature to fuse hydrogen to helium, guys. That's why protosun converts to what? Protosun converts to what? Sun. Later you will see that we have protostar. What is protostar? It is state of before formation of star. So protostar is cooler than the sun. The sun is hot. So protosun is cooler than protostar. When temperature increases, it reaches to what? It converts to what? So what is differences between star and protostar? Or what is differences between protosun and sun? The answer is this. Protosun or protostar makes energy by collision, correct? But sun, which it is a star or stars, they create energy by fusion. Protosun, protostar, temperature is around 7 to 8 million Kelvin. they gives IR, infrared spectrum, but the sun or star's temperature is actually 10 million Kelvin and more. So that is enough temperature to fuse hydrogen to helium. Make sense? So our sun actually in the core, the sun core's temperature is 15 million to 20 million Kelvin. So I go with minimum. And how old and what is the age of our solar system? Our sun is 4.6 billion years. 4.6 billion years. Guys, don't worry, our sun is young star. It's in the middle age actually. The lifetime of our sun is 10 billion years. We have close to 5 billion years. So it's in the middle age. After 2.5 to 3 billion years after today, the rate of hydrogen will be less than rate of helium in the sun. When that happens, the sun will start to expand because helium needs more temperature to fuse to other elements. When the sun expands, actually the mercury will fall inside the sun. I mean, it's not fall, the sun will expand and the sun will cover mercury until the mercury is level. And then the core of the sun will be very heavy, will be all iron, and the sun will collapse inside. When the sun gets collapsed, we will not see that day, but actually when the sun gets very hot, we will not have ocean in our planet. All oceans will be boiled, and our planet 3 billion years after today will be like Venus as it is today, extremely hot planet. Anyway, when the sun collapses, the sun will convert to a dwarf star, and the location of planets will completely change, and the most probably solar system will be smaller and smaller and smaller finally. Above this section, that what is the future of stars, what is the future of the sun, I will talk in chapter 10, 11, and 12. Okay. Now, what is fusion and what is fission? Let me finish this section and then I'll show you some PowerPoints. Look guys, so let me first of all explain you what is fission means. Also it's called fission. Also it's called fission or fission. In Greek language it's called fission. It's a Latin word actually. And fusion it's called fusion. Yeah, fission. This one is called fusion, fission. Okay. So what is fission means? It is nuclear process. It is nuclear process. What is that when we say it's nuclear process? Like nuclear bomb. Nuclear bomb. Nuclear power plant. So they make energy by fission. What is fission means? It's a nuclear process that heavy elements, so heavy elements converts to what? Lighter elements. This is called fission. Like uranium converts to plutonium. So heavy elements converts to lighter elements. During this process, some mass lost. Lost mass converts to energy. By what equation? By Albert Einstein equation, which E is equal with mc squared. What is m? It's mass, which is lost mass. And what is c? It's the speed of light. As you know, it's 3 times 10 to 8 meters per second. Let me explain you that. Watch, guys. Imagine you do have one apple, okay, for example, and this apple, let's say it is 2 kilogram. So the mass of this apple is 2 kilogram. Now we do nuclear process. What is nuclear process? If you change two important quantity, what they are. If you change pressure and if you change temperature. So if you increase pressure and if you increase temperature, so increase pressure, increase temperature, what is happening? The apple, after, process, it's not anymore apple. For example, it converts to orange, for example, okay? So these are like, let's say, orange. The element completely changes. Now, guys, when we measure mass of remained element after this process, we see the total mass is, for example, 1.8 kilogram. Okay, what I see here, I see, oh, differences in mass. How much is differences in mass? If I do 2 minus 1.8, the answer is 0.2, for example, okay? So where is this 0.2 kilogram? How? It is here. It's converted to what? Energy. By what equation? By E is equal what? mc squared. This m is this 0.2. This is what we do in nuclear bomb, what we do in nuclear power plant. We make fission, which is not clean energy because we have a lot of radioactivity, of course. Okay? And it's dangerous for our planet. Now, the second process, it's called fusion. It's called fusion. What is fusion? Fusion is opposite of fission. What do we have in fusion? Now let me give you another example. Look guys, at this time, let's say you have two small orange. Let's say they are orange, okay? And what we have, let's say this is, let's say it is 1 kilogram each one is, okay? So this is 1 kilogram and this one is also 1 kilogram, which total is 2 kilogram. So each particle, let's say it has 1 kilogram mass. Now, again, increase pressure and also increase temperature. When we increase pressure, when we increase temperature, we fuse these elements. Okay, so here we say we fuse orange, for example. Then what is conclusion? Pay attention. Conclusion becomes what? Apple, for example. When we measure mass of this apple, for example, it becomes what? 1.8 kilogram. Oh, look, two elements, two orange, they join together and we do some nuclear process, increase pressure, temperature, they join together, they make what? A different element. So if you see completely elements change, hydrogen converts to helium, helium converts to lithium, lithium converts to carbon, and then carbon converts to iron, goes to more heavy elements. This is fusion. This is fusion. What is happening? Watch. Lighter elements. So this is orange is 1 kilogram. This one is 1 kilogram. So lighter elements, they join together. They make heavy elements. Okay. What is happening? Guys, total mass of lighter elements, total was 2 kilogram. Now, what you have in the conclusion, you have 1.8 kilogram. Your single atom is heavier than single atom of this section, but your total mass again is less. Here is 1.8, here is 2 kilogram. Again, if you do 2 minus 1.8, the answer is 0.2. This is lost mass. This lost mass, again, by this equation, converts to energy. So this is energy. I want to give you good news. Fusion is clean energy. Y dot G. Fusion is clean energy. So stars, remember this, make energy by what process? By fusion. So what is happening in our star? Our star is the sun, guys. 4 hydrogen atoms. So these are all hydrogen. Hydrogen, hydrogen, hydrogen. 4 hydrogen atoms. They fuse, pressure increases, temperature increases, to 1 helium atom. During this, energy increases, energy releases. So the energy that we receive right now from the sun, it's actually because of fusion, because of 4 hydrogen atom, they fuse to 1 atom helium. During this process, some mass lost. That lost mass converts to what? Did you get this? So it is important. So what is differences between sun, protosun? Protosun gives you energy by collision of particles. Hydrogen to hydrogen makes collision. Helium to helium makes collision. So during this collision, IR forms. Let me give you one simple example. Look guys. When you clap, what is happening? Your hand gets hot, correct? So collision makes heat. When you hit your hand, your fingers on the table, you feel heat actually on your fingers. Why? Because collision makes heat. So that's in protosun. But what we have in the stars, in the sun, fusion. So all stars, they make energy by fusion of hydrogen to helium, majority of them. So I don't say all of them at this time, majority of them, yes. Later in chapters 11 and 12, when I go over mass of stars and temperature of stars and chemical composition of stars, over there we will see that it's not, in some stars, it's not hydrogen to helium. Helium converts to different elements. All right, so now let's go over some PowerPoints that I want to show you. Okay, look guys, let me see how can I do this. Yeah, so here was how the solar system formed, and I already explained. So let's go on this picture. Uh-oh. So in this picture, at the very beginning, we were, you have it in your book. It's also in chapter 6 in your PowerPoint, so please watch them. This is all same thing as I explained it. At the very beginning, we had solar nebula. Then because of collision, temperature increases, because of density increases, because of all gravity. So finally, at the center, the protosun forms, then protosun converts to the sun, then in the same time the other planets formed, and then planet formed, again planet formed, planetesimal, they stick together to make bigger planets. Finally we have what? Our solar system. You may ask, is Pluto part of planet or not? My answer is this. In 2003, the astronomers, the physicists, they decide to not call Pluto as a planet. Why? Because they defined as planet must be by itself, alone in its orbit. It must be big enough to have enough gravitational force to clear its orbit. Okay? Like for example, in planet Earth, it's only one planet Earth on its orbit. There is no second planet on its orbit. Okay? If it would be second planet, second rock, second thing on its orbit, we would say planet Earth is not planet anymore. So Pluto is not by itself. Pluto doesn't have enough gravity to attract the other rocks on itself, to itself, to so it cannot clear its orbit. Does it make sense? That's why they said, okay, let's not call Pluto as planet. But it is okay if you call it planet. Uh, the last news as I heard it, they want astronomers, they want to reclassify Pluto as planet. Okay, guys, so I want you to go over these PowerPoints. So here is formation of Jupiter, then formation of Saturn, then Neptune and Uranus. This is the picture that I was talking about. The process that planets, small planets, they stick together, it's called accretion. Accretion. Accretion means is accumulation of particles on each other to make the bigger particle. So here in this picture, you can see accretion of the inner planets, which if you see here, you have small planets, then after time, because of gravity, these small planets, they stick together, they make bigger planets. Then finally, those big small planets, they stick together to make one full planet on each level. This is called accretion. Okay, so accretion means is accumulation of particles or elements on each other to make bigger element. Here we have Kuiper belt and Oort belt, which they are beyond Neptunian orbit. So these will be as a essay, essay number 1 and 2. I will let you know about this. We will cover Kuiper belt and Oort belt in chapter 9 in your book in 11 edition, and chapter 8 in chapter 9 in 10 edition. Chapter 10 is in 11 edition. Okay, so these will be as essay for you. Another thing that I want you to pay attention, it's this, that the solar system is like a disk. Pay attention here, guys. Solar system is like plate, is like plane. This is very good picture. You can see the sun is at the center and all other planets are around the sun, but they are on one plate. They are on one, like plane. Let me explain you. So our solar system is like disk. It's called disk planetarium. Let me explain you that. Watch, guys. Solar system is like this. So let's say this is the sun, and then Mercury is here, okay? Then Venus is here, Earth is here, then Mars is here, then Jupiter is here, then Saturn is here, then Uranus is here, and Neptune is here. Let me make this as more beautiful. Okay, now it's okay. Okay, and Pluto is here. Watch it, guys. So how is disk? This is disk. They are all almost, I don't say absolutely 100%, but they looks like all on one line. They arranged. Pay attention. Mercury orbits the Sun, Venus orbits, Earth orbits, Mars, Jupiter, Saturn, Uranus, Neptune, and blah blah. So they are all on one line. If you stay here, if you look at the solar system, it's like one plane. I mean, it's not like this. Watch it. So if the Sun is here, Mercury is here, Venus is here, Earth is here, Mars is here, I don't know, Jupiter is here, Saturn is here, Uranus is here, Neptune is here. No, it's not like this. This is not a disk. This is not disk. So our planet is not like this. Our planet is like, sorry, our solar system is not, the planets are not scattered everywhere. No, they are actually on certain levels. Like what? Like if you remember last week, I did it in lecture. The atom. How is the atom, guys? Protons, they are inside the nucleus. Neutrons, they are also inside the nucleus. And then electrons, if you remember, as I said, they orbit on quantized levels, correct? So it's very similar to our planetarium disk. Okay? Chapter 6. No, sorry, let me go over this one. Here. Let me talk about this section, orbital characteristic of the planets. Here, Mercury is 0.39 AU. It takes 0.24 Earth year. It's like it takes 88 days that Mercury orbits the Sun. Venus is 244 days. Earth is 365 days. Mars is almost 2 years. So Mars is almost like 700 days that it takes for 680 something. 1 year on Mars is like 680 days. Look at the Jupiter. It takes 12 years almost, 11.86 years to orbit the Sun. Look at the Saturn, guys. It's 30 years takes one complete cycle. Uranus, 84 years, and Neptune is 164 years. Another important thing, let me explain you about the density. As I explained at the beginning of this lecture, density is mass divided by volume, correct? Look at this, guys. Mercury, Venus, Earth, Mars, they are called inner planets. Jupiter, Saturn, Uranus, and Neptune, they are called outer planets. Mercury, Venus, Earth, Mars, which they are inner planets, they are called terrestrial planets. They are all solid. Jupiter, Saturn, Uranus, Neptune, they are all gaseous planets. You cannot stay on Jupiter, on Saturn, on Uranus, on Neptune. You will go inside. But we can stay on Mercury, Venus, Earth, Mars. I want you to pay attention on density of these planets. Look, guys. Inner planets, Mercury, Venus, Earth, they are all in the range of 5,000, correct? So this is 5,400, this is 5,200, Earth is 5,500. Mars is a little less denser than the other planets in inner planets, 3,900. But these solid planets, they are dense. Which planet is the most denser planet? It's Earth. So Earth has the maximum density in our solar system, correct? In our planets. Jupiter is 1,300, Saturn is 690, Uranus 1,200, Neptune is 1,600. That's because of its core. So if you take a look, gaseous planets, they are all less dense. Water density is 1,000 kilogram per meter cube. Watch. Jupiter is 1,300, Uranus is 1,200, Neptune is 1600 kilogram per meter cube. So they are actually denser than water. They are denser than water. But Saturn has less density than water. That means this. If you have very big planet, and let's say that planet is made all by ocean, take the Saturn, put it on that planet, on the ocean, the Saturn will be floated on the water. Why? Because Saturn has minimum density. These are questions. Which planet has the minimum density in our solar system? Answer is Saturn. Which planet has the maximum density in our solar system? Answer is Earth. Okay, so this is about characteristic of planets, about the density. This is again, I defined it, its definition of density. Here is number of moons for each planet. Look, Mercury doesn't have moon, Venus doesn't have the moon, planet Earth fortunately has the moon, and one of the main reason in formation of the life on the planet Earth is moon. If moon wouldn't exist, for sure we would not have life on the Earth. I will explain you this one in next chapter actually. Yes. Mars has two moons. They are not sphere, they are like more potato. They are called Deimos, Phobos. I will talk about this in chapter 7 in inner planets. Jupiter has 69 moons. Watch, guys. Jupiter has 69 moons. In 2011, in your book, if you have like 9 edition or 8 edition, this number was 61. Now in new edition is 69. So Jupiter has 69 moons. But 4 of them, they are giant moons. Io, Europa, Ganymede, and Callisto. Again, I will go over this in chapter 8, which they are called Galilean moons. Saturn has 62 moons, Uranus has 27 moons, Neptune has 14 moons. Okay. And here is the summarization. So summarize of your PowerPoint. So I want you please to watch the video and also read these PowerPoints in chapter 6. Please read them, okay? Study them carefully, take the note. So chapter 6 done. So I want you to do homeworks, okay? Do homeworks chapter 6 in 11th edition, chapter 5 in 10th edition. Makes sense? I want you to do only review questions and advanced questions and what if. So I want you to do 17 first questions in chapter 6. You have 11 questions, it's review questions. 3 questions, they are advanced questions, and 3 questions, they are what if. So I want you to type them and make them as a PDF and send it to me, please, in your Canvas, please. So go in your Canvas, go to your inbox, attach it, send it to me in your Canvas, not to my email. They will show up in my email, but then, because I get bunch of emails from many wares, but when you go by your special in Canvas course, then I can figure out and I'm not gonna lost that email too. Okay? So I love you guys. Hope have a good week overall. Be safe, be healthy. Have a very good week. Bye.